You ever see a headline about some new drug, right? It's tested on just a few hundred people, and suddenly they're making these huge claims about how it affects millions. How do they do that? Well, it's not exactly magic, but it kind of feels like it. It's called statistical inference, and it is one of the most powerful ideas in all of science. So let's break down how it works.
Okay, let's make this real. Imagine a researcher develops a new diet. They have a hunch it affects blood sugar, but, they can't test every single person on Earth. They've only got a small sample, just 30 patients. So how in the world can they use that tiny group to make a credible claim about the diet's effect on everyone? This is the exact problem that statistical inference was designed to solve.
So here's our game plan for today. We're going to tackle this whole thing in 5 parts. First up, we'll set up our claim like a courtroom trial. Then, we'll meet the defendant, something called the Null Hypothesis. After that, we'll see how the verdict is reached using the p-value. And then, we'll go beyond a simple guilty or not guilty. And finally, we'll wrap it all up with what this all really means. So let's begin by stepping into what I like to call the statistical courtroom. The concept here is actually pretty simple. Every new scientific claim gets put on trial. And just like any good courtroom drama, it all comes down to the quality of the evidence. The fundamental challenge we're facing is that looking at the entire population is almost always impossible. So just like a prosecutor can't bring every single potential piece of evidence into the courtroom, a statistician can't survey every single person. What do we do instead? We take a random sample, a small slice, and we use that as our evidence.
Now, every courtroom needs a defendant. And in our statistical trial, that role is played by something called the Null Hypothesis. This is the central idea, the one in the hot seat, that we're going to put under scrutiny.
You can think of every statistical trial as a face-off between two competing ideas. On one side, you have the Null Hypothesis. We call it H0. This represents the status quo, the boring default assumption. In our diet example, it's the claim that this new diet does absolutely nothing. On the other side is the Alternative Hypothesis, or H1. This is the researcher's new exciting idea. Hey, I think this diet actually does have an effect.
So, this is the crucial point. We always start by assuming the null hypothesis is true. We assume the diet has no effect, just like a defendant is presumed innocent until proven guilty. The entire goal of our statistical test is to see if our sample data provides enough evidence to overturn that assumption, to prove guilt beyond a reasonable doubt.
So we have our defendant, the Null Hypothesis, and we have our evidence, the sample data. How do we decide the verdict? Well, that's where the most famous and, let's be honest, often misunderstood concept in all of statistics comes in, the p-value.
Let's break this down because it's important. The p-value answers a very specific question. If the diet really had no effect, if the null hypothesis were true, how likely is it that we'd see the results we saw in our 30 patients just by random luck? A tiny p-value means our results are super surprising and really unlikely to be a fluke. It's like finding the defendant's fingerprints all over the crime scene. It's strong evidence against their claim of innocence.
But, just like in a real court, juries can get it wrong. There are 4 possible outcomes. If the defendant is innocent, meaning the null is true, and we find them not guilty, that's a correct decision. Great. But if we convict them, that's a huge mistake called a type 1 error. On the flip side, if the defendant is actually guilty and we let them walk free, that's a type 2 error.
Let's be really clear about the stakes here. A type 1 error is like convicting an innocent person. It's a false alarm, where we claim an effect that isn't real. A type 2 error, that's letting a guilty person walk free. We missed an effect that was actually there. And honestly, statisticians are always trying to balance the risk of making these 2 different kinds of mistakes.
Okay, enough theory. Let's apply this to a concrete example. Imagine a claim is made. The true average weight of adults in a certain country is exactly 70 kilograms. We are going to put that claim on trial.
So here's how the case plays out. First, the claim on trial, our null hypothesis, is that the average weight is 70 kilograms. Next, our evidence. We take a sample of 100 people, and their average weight turns out to be 71.8 kilograms. Now we need to quantify how strong that evidence is. We do that by calculating a test statistic, a single number that summarizes the evidence, which in this case comes out to 2.02. Finally, we compare that to our threshold for guilt. To be 95% sure, our evidence score needs to be higher than 1.96.
And the verdict is in.
Since our evidence score of 2.02 is greater than the threshold of 1.96, we have enough proof. We officially reject the null hypothesis. We conclude that the claim that the average weight is 70 kilograms is likely false. Our sample data is just too far away from 70 to be explained by random chance.
So, case closed, right? Well, not exactly. A simple guilty or not guilty verdict can be a little unsatisfying. It really doesn't tell the whole story. This brings us to a different but very related statistical tool.
This is the key question. We've decided the average weight is not 70 kilograms. But that just leaves us wondering, well, what is it? Is it 71? Is it 72? Is it 70.1? A hypothesis test doesn't answer that. For that, we need a confidence interval.
And you know what? The idea behind a confidence interval is beautifully simple. You take your best guess from your sample, like that average weight of 71.8 kilograms, and then you just add and subtract a margin of error to create a plausible range. So, while a hypothesis test gives you a simple yes or no, is there an effect? A confidence interval gives you a range. It tells you, here is a set of plausible values for the true average weight based on our evidence. It actually quantifies the effect. It tells us how much of an effect there might be.
Let's look at another quick example. Say we tested a group's reading speed and found the average was 325 words per minute. Instead of just testing a claim, we can build a confidence interval around that number. And when we do the math, we might get a 95% confidence interval that spans from about 315 to 335 words per minute.
So what does that range actually mean? It means our best single guess is 325, but we're pretty confident the true average for the entire population is somewhere between 315 and 335. It gives us a sense of not just the effect size, but also our uncertainty about it.
Okay, we have been through a lot. Courtrooms, errors, intervals, the whole shebang. Let's bring it all together and focus on the two key questions these tools help us answer.
At the end of the day, you should think of these two tools as partners. The hypothesis test gives you that simple yes or no answer. Is there a real effect? Then, the confidence interval follows up with the crucial next question. Okay, if there is an effect, how big is it? So, what should you remember from all this? First, when you hear that phrase statistically significant, all it means is that the result is unlikely to be a random fluke. It does not mean the result is important or large or meaningful in the real world. That's why you should always ask about the size of the effect, and a confidence interval is one of the best ways to get that answer.
So I'll leave you with this final thought. Now that you know the difference between detecting an effect and measuring its size, you have a new superpower. The next time you read a news headline or a study that says a finding was statistically significant, what's the first question that's going to pop into your head? Hopefully it's something like, okay, but how big is the effect?